The universe is full of mysteries that defy everything we think we know. Imagine staring up at the night sky, where distant stars flicker like unanswered questions, each one hiding secrets that even our brightest minds can't fully explain. From the eerie silence of dark matter to the mind-bending paradoxes of black holes, space doesn't just challenge our understanding, it laughs in the face of it. And yet, here we are, humanity refusing to back down. Every unexplained phenomenon is a puzzle waiting to be solved, and today, we're diving headfirst into 30 of the most astonishing theories that could finally crack these cosmic riddles wide open. Some of these ideas will sound like science fiction whispers of parallel universes, hidden dimensions, and forces so strange they rewrite the rules of reality itself. Others might make you question whether we've been looking at the cosmos all wrong this whole time. What if the reason we can't find alien civilizations isn't because they're not out there, but because they're nothing like what we've been searching for? What if black holes aren't just cosmic vacuum cleaners but gateways to somewhere else? The more we learn, the clearer it becomes. Space isn't just mysterious. It's downright bizarre. That's why this journey is so thrilling. We're not just reciting facts, we're exploring the bleeding edge of human curiosity, where even the wildest guesses could be a step closer to the truth. Some of these theories might be proven right in our lifetime. Others might collapse under their own weight, only to spark even weirder ideas. But one thing's certain, by the time we're done, you'll see the universe in a whole new light. So buckle up, we're about to take off into the unknown, and trust me, you won't want to miss a single second of what comes next. Dark matter is the ghost in the cosmic machine, an invisible hand that sculpts the universe yet refuses to show itself. We know it's there because without it, galaxies would fly apart, stars would escape their orbits, and the entire structure of space would collapse. Think of it like wind. You can't see it, but you see the leaves it moves, the waves it stirs. Dark matter's presence is felt through its gravitational pull, bending light around galaxies and dictating the motion of celestial bodies with silent authority. Yet for all its influence, we still don't know what dark matter actually is. It doesn't emit, absorb, or reflect light, making it completely transparent to our telescopes. Some scientists believe it's made of undiscovered particles, strange and sluggish, drifting through space like an uncountable swarm of shadows. Others speculate it could be something even more exotic, tiny primordial black holes from the dawn of time, or even evidence of hidden dimensions leaking into our own. The hunt for dark matter has led to some of the most ambitious experiments ever conceived. Deep underground, in abandoned mines and beneath mountains, detectors wait for the faintest whisper of a dark matter particle colliding with ordinary matter. In space, telescopes map the distortions in starlight, tracing the unseen scaffolding that holds galaxies together. And while we haven't caught it yet, every failed attempt narrows down the possibilities, inching us closer to an answer. What makes dark matter so fascinating isn't just the mystery, it's the scale of its influence. This invisible substance makes up roughly 85% of all matter in the universe. That means everything we can see, stars, planets, even our own bodies, is just a fraction of what's really out there. The rest is hidden in plain sight, shaping the cosmos in ways we're only beginning to grasp. So why does dark matter refuse to reveal itself? Maybe we're looking in the wrong way, or maybe it operates by rules we haven't even imagined yet. Whatever the truth, one thing is certain. Solving this puzzle wouldn't just explain how galaxies form, it could rewrite our entire understanding of reality. And that's what makes the search so thrilling. Every unanswered question is a clue, every dead end a step closer to uncovering the universe's best-kept secret. If dark matter is the unseen scaffold holding galaxies together, dark energy is the mysterious force ripping the universe apart at the seams. Picture a cosmic tug-of-war where gravity tries to pull everything closer while something far more powerful pushes back, stretching space itself faster and faster with each passing moment. That's dark energy, the universe's ultimate accelerator, an invisible driver behind the most baffling discovery in modern cosmology, the fact that the expansion of the universe isn't slowing down. It's speeding up. This revelation came in the late 1990s when astronomers studying distant supernova made a shocking observation. These exploding stars, used as cosmic mile markers, were fainter than expected, meaning they were farther away than anyone predicted. The only explanation, the space between us and them was stretching faster over time, as if some unseen force was pressing down on the gas pedal of the cosmos. Overnight, dark energy went from theoretical speculation to a fundamental mystery shaping the fate of everything we know. What makes dark energy so perplexing is its sheer dominance. It makes up roughly 68% of the universe's total energy content, dwarfing both ordinary matter and dark matter combined. Yet, unlike gravity, which weakens with distance, dark energy's push seems to grow stronger as the universe expands, creating a runaway effect that could one day tear galaxies, stars, and even atoms apart in a theoretical Big Rip. Scientists are still grappling with what dark energy actually is. The leading candidate, Einstein's cosmological constant, a sort of energy woven into the fabric of space itself. But there's a problem. Calculations suggest its strength should be many orders of magnitude larger than what we observe. This colossal mismatch hints that we might be missing something profound, like an entirely new physics hiding in plain sight. Other theories propose that dark energy isn't constant at all but a dynamic field, evolving over time like an invisible fifth force. Some even suggest it's tied to extra dimensions or quantum fluctuations bubbling up from the vacuum of space. But with every telescope, simulation, and experiment, the mystery only deepens. Dark energy isn't just a curiosity, it's the key to understanding the universe's ultimate fate. Will expansion continue forever, leaving a cold, empty cosmos in its wake? Or could dark energy change its behavior, collapsing the universe back into a big crunch? For now, the answers remain as elusive as the force itself, reminding us that the universe still has secrets it isn't ready to give up. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing countless stars and planets. Given those staggering numbers, the odds seem overwhelming that life, even intelligent life, should exist somewhere beyond Earth. And yet, despite decades of searching, we've found no signals, no artifacts, not even a single microbe as proof. This glaring contradiction is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" One unsettling explanation is the Great Filter theory, the idea that somewhere between the emergence of life and the development of spacefaring civilizations, there's a nearly insurmountable barrier that wipes out intelligent species before they can spread across the cosmos. The terrifying question isn't just whether the filter exists, but where it lies. Are we incredibly lucky to have evolved past it, meaning most life gets wiped out earlier, perhaps during planet formation or the jump to multicellular organisms? Or is the filter still ahead of us, some catastrophic event like self-destruction through war or environmental collapse that prevents civilizations from reaching the stars? Then there's the zoo hypothesis, which suggests advanced civilizations might already know we're here but choose not to make contact, treating Earth like a protected wildlife reserve. Imagine ants in a forest unaware they're being observed by hikers. What if we're the ants and the hikers have decided not to interfere? This raises eerie questions about whether we're being studied, ignored, or deliberately quarantined for reasons we can't yet fathom. Other theories paint equally fascinating scenarios. Maybe interstellar travel is far harder than we think, with physics or energy limitations making long-distance communication impossible. Or perhaps civilizations inevitably turn inward, creating virtual realities so immersive they lose interest in the physical universe. There's even the dark forest hypothesis, that space is filled with silent, paranoid civilizations hiding, fearing that any broadcast could attract hostile attention from others. The Fermi Paradox forces us to confront not just the mysteries of space but our own future. If the universe is truly empty of intelligent life, what does that mean for humanity's fate? And if we're not alone, why does the cosmos feel so silent? Every unanswered signal, every barren exoplanet deepens the mystery, reminding us that the universe owes us no answers. But that's what makes the search so compelling, because the day we finally hear a reply, everything changes. Black holes have long been considered the ultimate cosmic dead ends, places where matter, light, and even the laws of physics seem to break down. But in the 1970s, Stephen Hawking dropped a bombshell that shattered this view. He proposed that black holes aren't entirely black after all. Instead, they slowly leak energy, emitting what we now call Hawking radiation. This revelation was revolutionary, suggesting that black holes could eventually evaporate, vanishing into nothingness over unimaginable stretches of time. But with this discovery came an even deeper puzzle. If a black hole disappears, what happens to all the information it swallowed? According to quantum mechanics, information can never truly be destroyed. Every particle, every interaction leaves a trace, like a cosmic fingerprint that should, in theory, be recoverable no matter what. But Hawking's calculations seem to show that when a black hole evaporates, the information inside it is lost forever, a direct contradiction to one of the most fundamental principles of physics. This clash became known as the black hole information paradox, and it sparked a decades-long battle between some of the brightest minds in science. One camp insists the information is irretrievably scrambled, erased from existence in a way that would force us to rewrite quantum theory. Others argue the data isn't gone, just hidden. Maybe it's encoded in the Hawking radiation itself, like a message encrypted in static noise. Or perhaps it's preserved on the black hole's event horizon, imprinted like a hologram on its surface. There's even a wild idea that the information escapes into an entirely separate universe, a hidden reality branching off from our own. The stakes couldn't be higher. If information truly vanishes, it undermines the foundation of modern physics. But if it's preserved in some unexpected way, we might be on the verge of uncovering a cosmic rulebook we never knew existed. Laboratories are simulating black holes with lasers and supercomputers, while theorists wrestle with equations that could bridge the gap between relativity and quantum mechanics. Some believe the answer lies in string theory or the holographic principle, where our three-dimensional reality is just a shadow of deeper, higher-dimensional truths. For now, the paradox remains unsolved, a tantalizing reminder that even the most extreme objects in the universe still hold secrets. Whether the information is lost, scrambled, or hiding in plain sight, one thing's certain: cracking this mystery wouldn't just explain black holes. It could reveal the hidden language of reality itself. What if everything we know, every star, every galaxy, even the laws of physics themselves, is just one version of reality among countless others? This is the mind-bending premise of the multiverse theory, the idea that our universe isn't the only one. Instead, it could be a single bubble in an endless cosmic foam, each bubble with its own unique rules, particles, and even histories. Some might have gravity so weak that planets never form, while others could be filled with exotic matter we can't even imagine. In some, life might thrive under conditions that would be impossible here. In others, time itself could flow backward. The roots of this idea stretch back to quantum mechanics, where particles exist in multiple states until observed, and to cosmic inflation, the theory that our universe expanded exponentially in the first fraction of a second after the Big Bang. If inflation can happen once, why couldn't it happen repeatedly, birthing new universes like bubbles in a boiling pot? string theory takes it further, suggesting that higher dimensions could harbor parallel realities, separated by membranes just out of reach. Critics argue that without a way to test these ideas, they're more philosophy than science. But supporters point to subtle clues like cold spots in the cosmic microwave background or unexplained gravitational anomalies as potential fingerprints of neighboring universes bumping against our own. Whether the multiverse is real or not, one thing's certain: it forces us to rethink our place in existence. If there are infinite versions of reality, does that make our universe more special or less? And if we're just one possibility among endless others, what does that say about the nature of reality itself? If black holes are the universe's ultimate cosmic vacuum cleaners, sucking in everything that crosses their path, then white holes are their bizarre opposites, theoretical fire hoses of existence, violently spitting out matter and energy instead of swallowing them. Born from the same equations of general relativity that predicted black holes, white holes are like a mirror image thrown into reverse, where the event horizon becomes an impassable exit rather than a point of no return. Picture a black hole's crushing grip, then flip it inside out. Instead of matter vanishing into darkness, it's being violently expelled into the cosmos in a torrent of radiation and particles. But here's the catch: white holes are purely hypothetical. No one has ever observed one, and many physicists argue they might not even be possible in our universe. Unlike black holes, which form naturally from collapsing stars, white holes would require some exotic mechanism to birth them, like a black hole running backward in time. Some theories suggest they could be the other end of an Einstein-Rosen bridge, better known as a wormhole, where matter sucked into a black hole in one corner of the universe is vomited out through a white hole in another. Others propose that the Big Bang itself could have been a white hole event, an explosion of space-time and energy so immense that it birthed everything we know. The most tantalizing idea comes from loop quantum gravity, which suggests that when a black hole reaches the end of its life and evaporates via Hawking radiation, it doesn't just fade away, it rebounds as a white hole in a spectacular burst of new creation. Imagine a dying star collapsing into a black hole, only to re-emerge billions of years later as a fountain of fresh matter, like a cosmic phoenix. It's a poetic idea, but the math behind it is still hotly debated. So why even entertain such a wild concept? Because white holes force us to question the very nature of causality, time, and the fabric of reality. If they exist, they'd rewrite our understanding of how matter and energy flow through the universe. They'd hint at hidden connections between distant regions of spacetime or even parallel universes. And if nothing else, they remind us that the cosmos is stranger than we can imagine, full of possibilities we haven't even begun to test. For now, white holes remain a dazzling thought experiment, a what-if scribbled in the margins of physics. But in a universe where black holes were once just mathematical curiosities before we found them lurking in the dark, who's to say white holes won't be the next great cosmic surprise? Until then, they stand as a reminder that the universe loves balance. For every ending, there might just be a new beginning waiting in the shadows. What if the universe isn't just something we observe, but something that responds to us? At the intersection of quantum mechanics and philosophy lies a radical idea. Consciousness might not merely perceive reality, but actively shape it. This concept, known as the participatory anthropic principle, flips our understanding of existence on its head. Instead of the universe unfolding independently, it suggests that conscious observers play a fundamental role in bringing reality into being. It's as if the cosmos waits for a mind to look at it before deciding what to be. The roots of this idea dig deep into quantum mechanics, where particles exist in a haze of probabilities until measured. Take the famous double-slit experiment. When unobserved, particles behave like waves, spreading out and interfering with themselves. But the moment a detector or human observer steps in, they snap into definite positions as if choosing a single path. This observer effect has puzzled scientists for decades. Is consciousness somehow collapsing these probabilities into reality? Or is there a deeper, weirder connection between mind and matter? Some theorists, like physicist John Wheeler, took this further with his participatory universe hypothesis. He imagined the cosmos as a self-excited circuit, where observers from humans to hypothetical alien civilizations retroactively define the universe's history by the mere act of witnessing it. In this view, the Big Bang might not have produced a finished reality but a spectrum of possibilities, with conscious beings completing the picture over billions of years. It's like a cosmic game of 20 questions where every observation narrows down what's real. Critics dismiss this as metaphysical speculation, arguing that observation in quantum physics simply refers to interactions between particles, not human awareness. Yet the mystery lingers. Why does the quantum world behave so differently when we're watching? Could there be layers of reality where mind and cosmos are inexplicably intertwined? Even if the link between consciousness and quantum mechanics remains controversial, the implications are staggering. If true, it would mean we're not just passive inhabitants of the universe, we're co-creators. Every measurement, every thought might ripple through the fabric of existence, shaping the cosmos in ways we're only beginning to glimpse. Whether this idea holds up to scrutiny or not, one thing's clear: the boundary between observer and observed is far blurrier than we ever imagined. And that's a mystery worth exploring to the very edge of understanding. What if life on Earth didn't actually begin here? The idea that life could hitchhike across the cosmos, riding on asteroids or comets like microscopic stowaways, isn't just science fiction. It's a serious scientific theory called Panspermia. Imagine a tiny microbe frozen in the void for millions of years, surviving the harsh radiation of space only to crash land on a young, fertile planet like Earth, sparking the chain reaction that led to us. It's a cosmic version of planting seeds in a garden, except the garden is the entire universe. The evidence for this isn't as far-fetched as it sounds. Take extremophiles, organisms that thrive in conditions we once thought were impossible. These hardy microbes flourish in boiling hydrothermal vents, radioactive wastelands, even the vacuum of space. If life can survive there, why couldn't it endure a journey between the stars? Experiments on the International Space Station have shown bacteria and tardigrades, tiny water bears, can withstand the vacuum, extreme cold, and deadly solar radiation for years. It's proof that life, at least in its simplest forms, is far tougher than we ever imagined. Then there's the discovery of organic molecules, the building blocks of life littered throughout space. Comets like 67P, studied by the Rosetta mission, contain amino acids and phosphorus, key ingredients for DNA. Meteorites recovered on Earth, like the Murchison meteorite, are packed with these same compounds. It's as if the universe is prepping the raw materials, scattering them like breadcrumbs across the galaxy. Even more tantalizing, in 2020, astronomers detected phosphine gas in Venus's atmosphere, a chemical often linked to microbial activity. Could it be a sign of life or just another clue in the cosmic delivery system? Panspermia comes in different flavors. Some scientists argue for ballistic panspermia, where impacts on one planet blast debris and any microbes clinging to it into space, eventually reaching other worlds. Others propose directed panspermia, the provocative idea that an advanced civilization might have deliberately seeded life like interstellar farmers. And then there's lithopanspermia, where life hides inside rocks shielded from radiation until it crashes into a new home. The biggest question isn't just whether life could travel this way, it's whether it did. If panspermia is real, life might not be rare at all. Instead, it could be a universal constant, a spark jumping from planet to planet whenever conditions allow. That would mean the story of life on Earth isn't just ours, it's part of a much grander tapestry, written across light years and billions of years. And if that's true, the search for extraterrestrial life isn't just about finding aliens. It's about finding our cosmic cousins. What if everything around us, every star, every atom, even the thoughts in your head isn't real, but an impossibly advanced simulation? This isn't just the plot of a sci-fi movie. It's a legitimate scientific and philosophical debate gaining traction in labs and lecture halls worldwide. The simulation hypothesis suggests our entire universe might be an artificial construct, a digital reality run by beings so advanced their technology is indistinguishable from what we'd call magic. And the scary part, we might never know the difference. The idea isn't new. Philosophers like Descartes pondered whether reality could be an illusion centuries ago. But in 2003, Oxford scholar Nick Bostrom gave it teeth with his famous trilemma, a stark set of possibilities. 1. Almost all civilizations go extinct before reaching technological maturity. 2. If they do advance, they lose interest in creating simulations. Or 3. We're almost certainly living in one. His reasoning: if even one civilization ever achieves the power to simulate conscious beings, they could create countless virtual worlds, making simulated minds vastly outnumber real ones. Statistically, the odds aren't in our favor. Look at our own technological trajectory. Just decades ago, video games were pixelated blips on a screen. Now, virtual reality can trick your brain into believing you're walking on Mars or battling dragons. AI is beginning to mimic human conversation so well, it's hard to tell who's real in a chat room. If this progress continues, creating a fully immersive simulation populated by conscious, self-aware beings might not just be possible but inevitable. So why couldn't we be someone else's experiment? Some physicists argue the universe itself gives clues. Ever notice how reality seems to run on tiny, indivisible units, quarks, electrons, pixels of spacetime? Quantum mechanics shows particles only snap into definite states when observed, almost like a computer rendering graphics only where you're looking to save processing power. Even the speed of light could be a built-in limit, preventing the simulation from overloading. And glitches. Some scientists point to anomalies in particle behavior or cosmic rays as potential bugs in the code. But not everyone's convinced. Critics say the hypothesis is unfalsifiable. It can't be proven or disproven, making it more metaphysics than science. Others argue that simulating every atom in a universe would require impossible amounts of energy, though proponents counter that an advanced civilization might use shortcuts, only simulating what's observed, like a video game loading distant terrain as you approach. The simulation debate forces us to confront eerie questions about existence. If we're just lines of code, do our choices matter? Could the simulators tweak the rules, or are we left to our own virtual free will? And if we one day create our own simulations, does that make us gods, or prisoners in an infinite loop of realities nested inside realities? Whether you find the idea terrifying or thrilling, one thing's certain: it blurs the line between science and philosophy in ways that keep us staring at the night sky, wondering if the stars are just someone else's screensavers. Time crystals sound like something ripped from the pages of a physicist's wildest dreams, structures that don't just exist in space, but pulse and repeat in time itself. Imagine a snowflake that doesn't just sit frozen on a window but dances in an endless loop, its atoms cycling through patterns without ever losing energy. That's the bizarre beauty of time crystals. They're the closest thing we've found to perpetual motion, defying one of the universe's most fundamental laws by oscillating indefinitely without any external input. The story begins in 2012 when Nobel laureate Frank Wilczek first proposed the idea, a radical twist on conventional crystals. Ordinary crystals like diamonds or quartz have atoms arranged in repeating spatial patterns. Time crystals flip this on its head, their atoms cycling through states in a fixed rhythm, like a cosmic metronome ticking forever without winding down. At first, critics dismissed it as impossible, a violation of thermodynamics. How could something move perpetually without energy? But by 2017, experiments with ion chains and diamond impurities proved time crystals weren't just theoretical. They were real, kicking off a revolution in how we think about matter and time. The secret lies in quantum entanglement, the eerie connection between particles that Einstein called spooky action at a distance. In a time crystal, entangled particles synchronize their oscillations, locking into a rhythm that repeats like clockwork, even in the lowest energy state. It's as if the universe left a hidden door open, allowing motion without energy, a loop that never winds down. Scientists have already created tiny versions in labs using lasers and magnetic fields, watching as these structures pulse with eerie precision, unfazed by friction or decay. But the cosmic implications are even wilder. If time crystals can exist naturally, perhaps in the crushing pressures of neutron stars or the strange quantum soup of the early universe, they might rewrite the rules of thermodynamics in extreme environments. Some theorists speculate they could be the key to quantum memory, offering flawless storage for futuristic computers. Others wonder if they're embedded in the fabric of spacetime itself, hidden patterns ticking away beneath reality like background code. The most mind-bending possibility, time crystals might blur the line between time and matter, suggesting that the flow of time isn't just a backdrop but something that can crystallize, fracture, or even be manipulated. What if the universe isn't just in time but made of it? For now, these questions hang in the air, tantalizing and unanswered. But one thing's certain, time crystals aren't just a laboratory curiosity. They're a glimpse into a deeper layer of physics where the ordinary rules break down and the universe starts to dance. The Big Bang marks the beginning of our universe as we know it, an explosion of space, time, and energy that set everything into motion nearly 14 billion years ago. But here's the twist, the Big Bang might not be the ultimate starting point. What if it was just one chapter in an endless cosmic saga, preceded by something even more mysterious? Scientists have spent decades wrestling with this question, and the answers they've come up with are as strange as they are fascinating. One compelling idea is the cyclic universe model, where the cosmos undergoes endless cycles of expansion and collapse, a cosmic heartbeat that never stops. Picture a universe expanding until gravity finally wins, pulling everything back into a fiery crunch. Instead of vanishing into nothingness, this collapse could trigger a rebound, a big bounce, where the compressed energy erupts into a new Big Bang, birthing a fresh universe from the ashes of the old. It's like a phoenix rising again and again, each cycle slightly different from the last, with new laws of physics or fundamental constants emerging every time. The math behind this is grounded in loop quantum cosmology, a framework that tweaks Einstein's equations to avoid the infinite density of a singularity. Instead of a definitive end, the universe reaches a maximum compression before quantum effects kick in, creating a repulsive force that reverses the collapse. Some versions of this theory even suggest traces of past universes could linger, cosmic fossils imprinted in the microwave background or the distribution of galaxies, subtle hints that we're not the first iteration of reality. Then there's the idea of a multiverse feeding into our Big Bang. Imagine a higher dimensional bulk where universes float like bubbles in foam, occasionally colliding. Our Big Bang could have been sparked by such a collision, a violent encounter with another universe that injected energy into empty space, igniting the expansion we see today. Some versions of string theory even propose that our universe is a membrane, or brain, that briefly touched another, releasing enough energy to kickstart everything. But the wildest theories go beyond physics into metaphysics. What if time didn't exist before the Big Bang? Without time, before might be meaningless, like asking what's north of the North Pole. The Big Bang wouldn't just be a beginning but the creation of time itself, a boundary where causality breaks down. Alternatively, our universe could be the offspring of a black hole in another reality, with the singularity of its collapse birthing our entire cosmos from the other side. While we may never know for sure, each theory forces us to rethink the nature of existence. Was the Big Bang a one-time event or just a ripple in an infinite ocean of universes? The answer could rewrite not just our cosmic history, but our understanding of reality itself. Neutron stars are the universe's ultimate pressure cookers, cosmic remnants so dense, a single teaspoon of their material would weigh more than a mountain on Earth. Born from the violent deaths of massive stars in supernova explosions, these objects squeeze protons and electrons together with such force that they merge into neutrons, forming a bizarre sea of ultra-compressed matter. But hidden in that crushing density might lie something even stranger, an exotic form of matter so unstable it could rewrite the rules of physics and pose a silent threat to anything that gets too close. This hypothetical substance is called strange matter, and it's thought to be a perfect, stable configuration of quarks, the fundamental particles that make up protons and neutrons. Under normal conditions, quarks are always bound together, never existing alone. But inside a neutron star's core, where pressures are 100 trillion times stronger than Earth's atmosphere, quarks might break free and reorganize into a soup of strange quarks, creating matter that's denser and more stable than anything in our universe. The terrifying part: if strange matter exists, it could be contagious. Here's where things get eerie. If a chunk of strange matter escaped a neutron star, say, through a collision or eruption, and came into contact with ordinary matter, it might trigger a runaway conversion. Like an atomic domino effect, the strange matter could transform everything it touches into more of itself, spreading relentlessly. Picture a single drop of this substance landing on Earth. Atoms in its path would unravel, their protons and neutrons dissolving into the strange quark soup. Given enough time, the entire planet could be rewritten at the most fundamental level, leaving behind a cold, dense sphere of pure strange matter. The idea isn't just speculative horror, it's grounded in real physics. Strange matter's stability comes from a quirk of quantum chromodynamics, the theory governing quarks. In extreme environments, strange quarks could have lower energy than ordinary matter, making them the universe's preferred state. Some models suggest certain neutron stars might actually be strange stars in disguise, their surfaces hiding cores of this exotic material. There's even a name for the hypothetical event where strange matter escapes, a strangelet catastrophe. Thankfully, the odds of this happening are astronomically slim. Neutron stars are incredibly distant, and strange matter, if it exists, would need to survive the journey through space intact. But the possibility raises profound questions about the nature of matter itself. Could the universe be silently filled with these ticking time bombs, remnants of dead stars waiting to rewrite reality? Or is strange matter just a fascinating quirk of math, a ghost in the equations with no real-world counterpart? For now, the mystery endures. Telescopes scan neutron stars for clues, while particle colliders like the Large Hadron Collider hunt for fleeting glimpses of strange quark matter in high-energy collisions. Whether strange matter is out there or not, its very concept forces us to confront how little we truly understand about the extremes of the cosmos, and how even the most exotic theories might one day prove terrifyingly real. Imagine crossing the galaxy in an instant, bypassing light years of empty space as if stepping through a hidden doorway. This is the promise of Wormholes, hypothetical tunnels carved into the fabric of spacetime itself, offering shortcuts between distant points in the universe. Known in physics as Einstein-Rosen bridges, these cosmic passageways emerge straight from the equations of general relativity, where the warping of space and time can, in theory, create a bridge between two black holes or even separate universes. The concept is as elegant as it is mind-bending. Picture spacetime as a sheet of paper. Normally, traveling from one side to the other means crossing the entire length. But if you fold the paper, bringing two distant points together, a wormhole would be like poking a pencil through the fold. a direct route bypassing the space in between. Einstein and physicist Nathan Rosen first explored this idea in the 1930s, revealing that black holes might not be dead ends but potential gateways, their singularities connecting to mirrors of themselves on the other side. But here's the catch: wormholes as described by relativity would be catastrophically unstable. The moment they form, the intense gravitational forces at their cores would snap them shut faster than light could pass through, collapsing the tunnel before anything or anyone could make the journey. To keep a wormhole open long enough to traverse it, you'd need something to prop it open against the crushing weight of spacetime itself. That's where exotic matter comes in, a hypothetical substance with negative energy, behaving in ways that defy common sense. Unlike normal matter, which attracts via gravity, exotic matter would repel, acting like cosmic scaffolding to prevent the wormhole's collapse. The problem: exotic matter has never been observed in nature. Quantum mechanics hints that tiny amounts of negative energy might exist fleetingly in the vacuum of space, but the quantities needed to stabilize a traversable wormhole are staggering. Some theories suggest advanced civilizations could harvest this energy, manipulating quantum fields to construct permanent shortcuts. Others argue that wormholes might exist naturally, but only at microscopic scales, woven into the quantum foam of spacetime, far too small for any practical use. Even if we could overcome these hurdles, wormholes come with other, stranger complications. Time dilation near their mouths could mean that exiting one end might catapult you into the distant future, or even the past, raising paradoxes that make physicists shudder. And then there's the blue sheet problem. The moment you try to pass through, the accumulated energy of even a single photon could destabilize the tunnel, triggering a collapse mid-journey. Yet, despite these challenges, wormholes remain a tantalizing possibility. They offer more than just interstellar travel. They're potential keys to understanding the deeper structure of reality. Could they explain the universe's hidden symmetries or the mysteries of quantum entanglement? Might they be the universe's natural subway system, silently connecting distant regions we've yet to explore? Until we find one, or prove they can't exist, wormholes will keep fueling our wildest cosmic dreams, reminding us that the universe might still have shortcuts waiting to be discovered. Imagine the universe as a frozen lake on a bitter winter morning, seemingly solid, stable, but hiding a fragility beneath the surface. Now picture a single crack forming in that ice, racing outward in all directions, shattering everything in its path. That's the essence of vacuum decay, a cosmic doomsday scenario where the very fabric of reality could unravel in an instant, rewriting the laws of physics as we know them. It all hinges on a terrifying possibility that the universe isn't in its truest, most stable state, but teetering on a precarious ledge, a false vacuum, just waiting to collapse into something deeper and darker. Here's how it works. According to quantum field theory, what we call empty space isn't empty at all. It's a seething quantum foam buzzing with potential energy. Most of the time, this energy sits at its lowest possible state, the true vacuum. But what if our universe isn't in that true vacuum? What if we're stuck in a higher energy false state, like a ball balanced on a hill, just waiting for the slightest nudge to roll downhill into oblivion? If that shift were to happen anywhere in the cosmos, it would create a bubble of true vacuum that expands at the speed of light, obliterating everything in its wake. The effects would be beyond catastrophic. As the bubble expands, the fundamental constants of nature, the strength of gravity, the behavior of atoms, even the speed of light, would change irrevocably inside it. Matter as we know it would cease to exist. Stars, planets, and life itself would disintegrate into a new reality governed by alien physics. The worst part: there'd be no warning. One moment, everything's normal. The next, an invisible wall of annihilation races toward us at light speed, leaving no time to react, no chance to escape. Theoretical physicists take this seriously because the math doesn't rule it out. In fact, the Higgs field, the same field that gives particles mass, might be the smoking gun. Measurements suggest it's just stable enough to sustain our universe for now. But if a high-energy event like a cosmic ray collision or a particle accelerator experiment tips the balance, it could theoretically trigger the cascade. Some models even suggest vacuum decay could have already started somewhere in the distant cosmos, its wave of destruction silently barreling toward us across billions of light years. Yet there's a strange comfort in this existential terror. If vacuum decay is possible, it's likely so improbable that we'll never witness it. The universe has lasted nearly 14 billion years without collapsing, hinting at remarkable stability. Still, the mere possibility forces us to confront how delicate reality might truly be, and how lucky we are to exist in this fleeting pocket of cosmic equilibrium. Whether vacuum decay remains a thought experiment or a lurking threat, one thing's certain: it's a chilling reminder that the universe owes us nothing, and every moment of existence is more fragile than we dare admit. When Oumuamua streaked across our solar system in 2017, it didn't just break the rules, it tore up the cosmic rulebook entirely. This strange, tumbling object was the first confirmed visitor from interstellar space, arriving faster and leaving faster than anything we'd ever seen. Its bizarre trajectory, unexpected acceleration, and peculiar shape somewhere between a cigar and a pancake left scientists scrambling for explanations. But here's the real mystery. Was it just an oddly shaped space rock or something far more deliberate? At first, astronomers assumed Oumuamua was a comet. But unlike comets, it showed no visible tail, no outgassing of material as it neared the sun. Then came the kicker: it accelerated as it hurtled away, as if pushed by an unseen force. Comets do this when sunlight vaporizes their ice, creating a propulsive jet, but Oumuamua left no detectable debris. So what was nudging it forward? Some researchers pointed to a wild possibility. Maybe it wasn't natural at all. Harvard astrophysicist Avi Loeb famously suggested Oumuamua could be artificial, a discarded piece of alien technology, perhaps a broken solar sail drifting between the stars. The idea wasn't entirely baseless. A thin, reflective object like a solar sail could explain Oumuamua's bizarre acceleration, catching sunlight like a cosmic windsock. Its unusual shape, flat and elongated, would also fit the profile of a designed object, engineered to minimize collisions with interstellar dust. Even its tumbling motion could hint at a derelict craft, spinning aimlessly after its propulsion failed. Skeptics rolled their eyes, but the truth is, we've never seen anything like it before, and that alone makes the question worth asking. Then came the counter-arguments. Could Oumuamua be a chunk of frozen nitrogen, broken off from a distant Pluto-like world? When nitrogen warms, it sublimates directly from ice to gas, potentially producing thrust without visible debris, perfectly matching the object's behavior. Others proposed it might be a hydrogen iceberg, a fragile relic from the coldest depths of space, glowing faintly as it evaporated. The problem: hydrogen ice should have vaporized long before reaching our solar system. The debate rages on because Oumuamua is already gone, vanishing into the void before we could get a close look. Future telescopes might spot more interstellar visitors, but for now we're left with tantalizing uncertainties. Was this our first brush with alien engineering, or just a cosmic oddball, a freak of nature we don't yet understand? The answer could redefine how we see the universe, whether it's filled with civilizations leaving breadcrumbs or simply stranger rocks than we ever imagined. Quantum entanglement is one of the most baffling, beautiful phenomena in the universe, a ghostly connection between particles that defies everything we know about distance and reality. Picture two electrons born from the same atomic event, spinning in perfect sync no matter how far apart they drift. Change the spin of one, and its partner instantly reacts, as if whispering across the void faster than light itself. Einstein called this spooky action at a distance, and for decades, physicists wrestled with the implications. Because if information can truly leap between entangled particles faster than light, it throws a wrench into the cosmic speed limit set by relativity. But what if we could harness this eerie connection to revolutionize communication across the stars? The implications for space exploration are staggering. Right now, sending a signal to Mars takes anywhere from 4 to 24 minutes, depending on the planet's positions. Imagine controlling a rover or speaking with astronauts in real time with no lag. Entanglement could make it possible. The idea hinges on quantum teleportation, where the state of one particle is transferred to its entangled partner, effectively beaming information without physical travel. Labs have already done this over fiber optic cables and even via satellite, proving it works over hundreds of miles. Scale that up, and you've got an interstellar comms network where messages cross light years in the blink of an eye. But here's the catch: entanglement doesn't actually break the speed of light. As weird as it seems, the particle states are correlated instantly, but you still need a conventional signal, say a radio wave, to decode the message. It's like having twin dice that always land on matching numbers, but someone still has to call you and tell you what theirs rolled. That's why some scientists argue faster than light communication is impossible, no matter how entangled your particles are. Yet others aren't so sure. Alternative theories like retrocausality suggest quantum effects might reach backward in time, tweaking probabilities before measurements are made. Could we exploit that to cheat the system? The wildest possibility is that entanglement hints at a deeper layer of reality, where distance is an illusion. Some interpretations of quantum mechanics propose that all particles are fundamentally connected through hidden dimensions or a universal quantum field. If true, space exploration wouldn't just be about crossing physical distances, it'd be about tapping into the invisible threads stitching the cosmos together. Even if we never crack faster than light travel, entanglement might still offer unbreakable encryption for interstellar messages or ultra-precise navigation using quantum sensors. For now, the dream remains just out of reach, tangled in paradoxes and technical hurdles. But every experiment inches us closer to bending the universe's rules in ways Einstein never imagined. Whether we're on the verge of a quantum revolution or chasing shadows, one thing's clear: the cosmos is far stranger than we think, and the answers might be hiding in the silent dance of entangled particles. What if everything we perceive, every star, every atom, even the sensations in our own minds, isn't truly three-dimensional but an elaborate illusion, like a cosmic mirage painted across the surface of something far stranger? This is the startling premise of the holographic universe theory, the idea that reality as we know it might be nothing more than a two-dimensional projection, a shadow play cast from the edges of space itself. It sounds like science fiction, but the roots of this idea sprout from the hardest corners of physics: black holes, string theory, and the fundamental limits of information in the cosmos. The story begins with black holes, those gravitational monsters that swallow light and twist space-time into knots. In the 1970s, physicist Jacob Bekenstein made a revolutionary discovery. Black holes have entropy, a measure of disorder that's inextricably linked to their surface area, not their volume. This was bizarre. In everyday objects, entropy scales with how much stuff is inside them. The more volume, the more disorder. But black holes defy this logic, suggesting the information they contain isn't stored in their depths but smeared across their event horizons like data encoded on a celestial hard drive. Then came Stephen Hawking, who showed black holes slowly evaporate, leaking radiation until they vanish. But if the information inside them is truly trapped, where does it go? The answer, according to the holographic principle, is that it never left, because the three-dimensional interior was just an illusion all along. String theory takes this even further. In the 1990s, physicist Juan Maldacena proposed a mathematical universe where gravity in a five-dimensional space could be perfectly mirrored by quantum particles living on its four-dimensional boundary, a holographic duality where two radically different realities describe the same physics. Suddenly, the idea that our 3D world might be a projection from a lower dimensional surface wasn't just plausible, it was mathematically elegant. Think of it like watching a movie on a screen. The images appear to have depth, but every detail is actually encoded in flat pixels. If the universe works this way, then every galaxy, every thought, every law of physics might just be data written on some vast, unseen surface we can't perceive. So where's the proof? Some scientists point to the cosmic microwave background, the afterglow of the Big Bang, searching for subtle pixelation or noise that might betray the universe's true resolution. Others argue that quantum entanglement, where particles instantly influence each other across vast distances, could be a side effect of this deeper, connected reality. Even gravity's stubborn resistance to being unified with quantum mechanics might hint that it's not a fundamental force at all, but an emergent phenomenon, a side effect of information processing on the cosmic horizon. The implications are staggering. If the holographic principle holds, then free will, time, even consciousness might be secondary features of a reality that's fundamentally simpler than it appears. It would mean the universe is a kind of cosmic optical trick, a grand illusion where nothing is lost or destroyed, just transformed from one layer of the hologram to another. And while we're far from definitive evidence, the mere possibility reshapes how we see existence itself, not as a vast, solid thing, but as a shimmering projection, a story written on the skin of the unknown. Beyond the known worlds of our solar system, lurking in the frigid darkness past Neptune, something massive may be pulling strings, tugging at the orbits of distant objects with an invisible gravitational hand. Astronomers call it Planet 9, a hypothetical giant that could rewrite our solar system's map if it's real. The evidence isn't direct, no one's seen it yet, but the clues are etched into the strange paths of icy bodies drifting far beyond Pluto. These objects don't move randomly, their orbits cluster in ways that defy probability, as if an unseen force herded them into alignment. The story begins with the Kuiper Belt, that ring of frozen leftovers from the solar system's birth. Most objects there follow predictable orbits, but a handful, like the dwarf planet Sedna, trace bizarre, elongated paths swinging inexplicably far from the Sun. Then, in 2016, astronomers Konstantin Batygin and Mike Brown noticed something even weirder. 6 of these objects tilted at similar angles, their closest approaches to the Sun bunched together. The odds of this happening naturally, less than 1 in 14,000. Their conclusion, a planet 10 times Earth's mass, orbiting 20 times farther than Neptune, must be shepherding them. The hunt for Planet 9 is a cosmic detective story, piecing together clues from gravitational fingerprints. If it exists, it's likely a frozen super-Earth or a mini Neptune, reflecting so little sunlight that current telescopes struggle to spot it. Yet its influence is everywhere. The Cassini spacecraft orbiting Saturn detected slight anomalies in the planet's path, tiny wobbles that could hint at Planet 9's pull. Even the tilt of the Sun's axis might betray its presence. Simulations show such a distant heavyweight could nudge the entire solar system off kilter over billions of years. Searches are underway with some of the world's most powerful telescopes, like Subaru in Hawaii, scanning the sky for a faint dot moving against the stars. The challenge, Planet 9's orbit could take 10 to 20,000 years to complete, meaning it might be anywhere along a vast, slow path. Some researchers suggest looking for heat signatures with infrared telescopes, while others propose tracking its gravitational ripples on more distant objects yet to be discovered. But skepticism lingers. Could the odd orbits be a fluke or caused by multiple smaller objects? Some simulations suggest a primordial black hole, no larger than a grapefruit but as massive as a planet, could explain the data. Others argue the anomalies stem from observational bias. We've only mapped a fraction of the Kuiper belt, and more data might dissolve the mystery. Whether Planet 9 is a hidden giant, a swarm of debris, or something even stranger, its pursuit is more than a celestial scavenger hunt. Finding it would redefine our solar system's architecture, proving there are still giants lurking in the dark. And if it's not there, the search itself has already revealed how much we've yet to learn about the wild frontier beyond Neptune, where the rules of gravity and chaos dance in ways we're only beginning to understand. In the vast emptiness of space, where time stretches into eternity and matter is spread impossibly thin, the laws of physics allow for something utterly bizarre: a single, disembodied consciousness blinking into existence, fully formed with memories and senses, only to vanish moments later. This is the unsettling premise of the Boltzmann brain paradox, a thought experiment so strange it threatens to undermine our most basic assumptions about reality. Named after physicist Ludwig Boltzmann, who first grappled with the statistical nature of entropy, the theory suggests that in an infinite universe, even the most improbable events must eventually occur, including the spontaneous formation of self-aware minds in the void. Picture this: over trillions upon trillions of years, quantum fluctuations in the vacuum of space could, by sheer chance, arrange particles into a functioning brain complete with fabricated memories of a past that never was. This brain might experience a fleeting moment of awareness, perhaps remembering a life on Earth, the warmth of sunlight, the sound of laughter, only to dissolve back into chaos. According to probability, these random, self-aware fluctuations should be vastly more common than entire ordered universes like ours. After all, it's far easier for particles to randomly assemble a single conscious moment than to construct galaxies, planets, and billions of years of evolution. The implications are staggering. If Boltzmann brains are possible, how can we trust that our own consciousness isn't one of these statistical flukes? Our memories, our sense of history, even the laws of physics we observe could be illusions conjured by a momentary accident in the cosmic dark. Modern cosmology recoils at this idea, not just because it's unsettling, but because it throws the scientific method into crisis. If reality could be a hallucination of a transient brain, then all our observations, from the fossil record to the cosmic microwave background, might be nothing more than a convincing dream. Physicists have proposed ways to dodge this paradox. Some argue that the accelerating expansion of the universe, driven by dark energy, will eventually make even quantum fluctuations impossible, cutting off the supply of potential Boltzmann brains. Others suggest that the multiverse theory rescues us if infinite universes exist. The sheer number of real, conscious beings would outweigh the statistical noise of random ones. But the debate rages on because the problem isn't just about physics, it's about the nature of existence itself. Are we the products of a grand cosmic narrative, or just temporary ripples in an indifferent void? What makes the Boltzmann brain paradox so haunting isn't just the science, it's the way it worms into our deepest fears about identity and meaning. It's the ultimate existential prank, a cosmic joke where the punchline might be that nothing is truly real. And while the odds of us being Boltzmann brains are vanishingly slim, the theory forces us to confront a humbling truth. In an infinite universe, even the impossible might be inevitable. Whether a disturbing footnote or a fundamental challenge to reality, the Boltzmann brain remains one of cosmology's most mind-bending puzzles. A reminder that in the grand scheme of things, we understand far less than we think. Somewhere beyond the edge of the observable universe, an invisible force appears to be pulling entire galaxy clusters in the same direction at staggering speeds, as if the cosmos itself is caught in a river with no source. Astronomers call this phenomenon dark flow, and it's one of the most perplexing mysteries in modern cosmology. Imagine throwing a handful of leaves into a stream. They'd all drift together, carried by the current. Now picture that happening with galaxies millions of light years across, all moving toward some unseen destination beyond our cosmic horizon. That's dark flow in action, a tantalizing hint that there's more to the universe than what we can see. The discovery came in 2008 when scientists studying the cosmic microwave background, the afterglow of the Big Bang, noticed something bizarre. Hundreds of galaxy clusters weren't just expanding with the universe, they were racing in a specific direction at over 2 million miles per hour, as if dragged by an immense gravitational pull. At first, researchers thought it might be an error, but repeated observations confirmed the pattern. These clusters, scattered billions of light years apart, were caught in a synchronized drift toward a single point in space, a place with no known supercluster or cosmic structure massive enough to explain the motion. What could possibly exert such a pull? One radical theory suggests the clusters are feeling the gravitational tug of something beyond our observable universe, perhaps another universe brushing against ours in the vast multiverse. Just as the moon's gravity creates Earth's tides, a neighboring universe might be warping spacetime on a scale we can't comprehend, leaving this eerie current as the only clue. Others propose the existence of a colossal, unseen structure, a massive overdensity of matter so vast it defies our models of cosmic distribution. Picture a mountain range so enormous, its shadow stretches beyond the horizon. We can't see the peak, but we feel its pull. Then there's the unsettling possibility that dark flow challenges the cornerstone of modern cosmology, the cosmological principle, which states that the universe should look roughly the same in all directions on large scales. If galaxy clusters are streaming toward a single point, it implies an asymmetry, a cosmic special direction that shouldn't exist. Some theorists argue this could mean our universe isn't uniform at all but tilted or lopsided in ways we're only beginning to detect. Skeptics counter that dark flow might just be an illusion, a statistical fluke or measurement error amplified by incomplete data. But as telescopes grow more precise, the signal persists, whispering of forces we can't yet name. Whether it's evidence of parallel realities, hidden dimensions, or flaws in our understanding of gravity, dark flow reminds us that the universe still holds cards it hasn't revealed. And if we ever trace this cosmic river to its source, we might find not just answers but questions we never thought to ask. Hidden behind the thick veil of stars and dust along the plane of our Milky Way, a cosmic heavyweight is bending the paths of entire galaxies toward it. An invisible force so powerful, it's dragging us along for the ride at over 14 million miles per hour. Astronomers call it the Great Attractor, and its existence rewrites the map of our galactic neighborhood. This gravitational anomaly sits roughly 250 million light-years away in the direction of the constellation Centaurus, yet its true nature remains one of the most tantalizing unsolved puzzles in modern astronomy. For decades, scientists struggled to study it directly because our own galaxy's disk, packed with gas, dust, and billions of stars, blocks the visible light from whatever lies beyond. It's like trying to spot a lighthouse through a blizzard. No matter how bright the beam, the storm swallows it whole. But in the 1970s, researchers noticed something bizarre. Galaxies in our local supercluster, including the Milky Way, weren't just drifting apart with the universe's expansion. They were all being pulled toward the same mysterious point in space. The Great Attractor wasn't just a curiosity, it was a cosmic magnet reshaping the motion of everything around it. What makes this enigma even stranger is the scale of its influence. The Great Attractor's gravitational pull suggests it should contain the mass of tens of thousands of Milky Ways crammed into a relatively small region of space. Yet when astronomers peered through the interstellar fog using X-ray and infrared telescopes, they found something unexpected. The mass didn't match. There wasn't enough visible matter, no colossal galaxy cluster, no titanic black hole to explain the staggering gravitational tug. This led to two spine-tingling possibilities. Either we're missing something fundamental about how gravity works on cosmic scales, or the Great Attractor is just the tip of something far larger lurking in the shadows. Then came an even bigger surprise. In the 21st century, astronomers mapped the motion of galaxies beyond the Great Attractor and discovered an even more massive structure, the Shapley supercluster, a sprawling metropolis of galaxies over 650 million light-years away. Some believe Shapley's gravity might be amplifying the Great Attractor's pull, like a hidden hand behind the curtain. Others speculate the Great Attractor itself is part of a vast, interconnected web of dark matter. Filaments of invisible mass knitting the universe together in ways we're only beginning to trace. The deeper we look, the more questions arise. Could the Great Attractor be a dense knot in the cosmic web, where dark matter flows like rivers converging? Or is it a sign of larger structures, superstructures so immense they challenge our understanding of how the universe organizes itself? Every new observation peels back another layer, revealing just how much we don't know about the forces sculpting our corner of the cosmos. One thing's certain, the Great Attractor isn't just pulling galaxies, it's pulling us closer to a revelation. Whether it's a beacon pointing to deeper mysteries or a cosmic accident of gravity, its existence reminds us that even in our own backyard, the universe is still full of secrets waiting to be uncovered. And as technology pierces through the Milky Way's dusty curtain, we might finally glimpse what's been tugging at us all along. When a star goes supernova, it's supposed to be the ultimate cosmic finale, a catastrophic explosion that obliterates the star so completely, nothing remains but an expanding cloud of debris. But in the darkest corners of the universe, some stars refuse to die quietly. Meet the zombie stars, celestial survivors that endure supernova only to stagger on, mangled and luminous, defying every textbook model of stellar death. At the heart of this cosmic horror story is one of the strangest supernova variants ever discovered, the type IX. Unlike its more famous cousin, the type Ia, which completely annihilates a white dwarf, the IX is a fainter, weaker explosion that somehow leaves behind a battered, half-dead remnant. Picture a stellar explosion that doesn't quite stick the landing. Instead of tearing the star apart completely, the supernova's shockwave rips through it unevenly, blasting away some layers while leaving a scarred, shrunken core still burning in the wreckage. These zombie stars aren't just theoretical oddities, astronomers have spotted them. Take supernova 2008 Ha, the first confirmed survivor. Normally, a white dwarf supernova leaves nothing behind, but in this case, telescopes detected a stubborn, luminous object still clinging to existence in the blast zone. This wasn't a ghostly neutron star or black hole, the usual supernova leftovers, but a damaged white dwarf, somehow still fusing elements despite enduring an explosion that should have erased it entirely. How does a star cheat death like this? The leading theory points to a cosmic heist gone wrong. Type IX supernova likely occur in binary systems where a white dwarf siphons material from a companion star, growing until it hits a critical mass and detonates. But unlike a classic type Ia where the entire star detonates symmetrically, the IX might be a failed explosion, a partial ignition that doesn't fully consume the star. Imagine lighting a firework that fizzles halfway through. The outer layers blow off, but the core remains intact, scorched and disfigured. These zombie stars are left with bizarre compositions, their surfaces littered with the fallout of their own near-death experience. Elements like neon, oxygen, and carbon forged in the blast but never fully ejected. The existence of these stellar undead forces astronomers to rethink how stars die. If white dwarfs can survive supernova even in mangled form, how many other supernova variants might we be missing? Could there be even stranger remnants lurking in the wreckage of seemingly ordinary explosions? And what happens to these zombies over time? Do they cool into inert husks, or might they reignite in some unexpected way? Every new discovery peels back another layer of mystery, proving that even in the violent chaos of stellar death, nature has a few surprises left. One thing's for certain, zombie stars aren't just cosmic oddities. Their clues messy, contradictory, and utterly fascinating, that our understanding of stellar life cycles is still far from complete. Whether they're rare flukes or the tip of an unseen iceberg, their very existence pushes the boundaries of astrophysics, forcing us to rewrite the rules of how stars live, die, and sometimes refuse to stay dead. In the depths of space, mysterious pulses of radio energy erupt with the power of hundreds of millions of suns blasting across the cosmos in mere milliseconds before vanishing without a trace. These are fast radio bursts, some of the most enigmatic signals ever detected, and their origins have sparked a cosmic detective story spanning neutron stars, colliding black holes, and even the faint possibility of something far more deliberate. When astronomers first stumbled upon these bursts in 2007, they seemed like cosmic glitches, random blips too powerful and too brief to make sense. But as more were discovered, a pattern emerged. These weren't accidents. They were messages from the universe, written in a language we're still struggling to decode. The leading suspects, magnetars, ultra-dense, highly magnetized corpses of dead stars spinning with such ferocity that their magnetic fields could crack planets. Picture a cosmic lighthouse, but instead of light, it's blasting beams of radio waves so intense they briefly outshine entire galaxies. In 2020, astronomers caught one red-handed. A magnetar in our own galaxy erupted with a burst strikingly similar to a fast radio burst, offering the first solid clue that these exotic objects might be behind at least some of these signals. But here's the twist: not all bursts fit the magnetar mold. Some repeat at irregular intervals, while others appear just once, leaving no trace of their source. Then there's the collision theory. When two neutron stars spiral into each other, their cataclysmic merger could unleash a shockwave of radio energy as their magnetic fields snap and twist. It's a violent, one-time event, perfect for explaining non-repeating bursts, but the math doesn't always add up. The energy required is staggering, and we've yet to catch a burst in the act of such a collision. Even stranger are the bursts with bizarre, almost rhythmic repetition, like cosmic heartbeats. Could these be the death throes of exotic objects we've never seen, like quark stars or cosmic strings, theoretical remnants of the early universe? Of course, no discussion of fast radio bursts would be complete without the elephant in the room: alien technology. The bursts' precision and intensity have led some to wonder if they could be artificial. Perhaps signals from an advanced civilization, or even the byproduct of massive interstellar light sails harnessing radio waves for propulsion. While most scientists consider this a long shot, the sheer unpredictability of these bursts means we can't rule anything out. After all, history has taught us that the universe is often stranger than our wildest guesses. What makes fast radio bursts so thrilling isn't just their mystery, it's what they reveal about the cosmos. As these signals travel billions of light years, they interact with the sparse matter between galaxies, letting astronomers map the universe's hidden structure like cosmic sonar. Each burst is a fingerprint carrying clues about the environments it's passed through. And with new telescopes like the Canadian Hydrogen Intensity Mapping Experiment and the upcoming Square Kilometre Array, we're on the verge of catching hundreds more, turning these cosmic whispers into a chorus. Whether they're the screams of dying stars, the echoes of collisions, or something beyond our current understanding, one thing's clear: fast radio bursts are more than just celestial static. They're a reminder that the universe is alive with phenomena we've only begun to glimpse, and every new detection brings us closer to rewriting the story of the cosmos itself. Imagine an alien astronomer light years away pointing their telescope at Earth, analyzing the faint glow of our atmosphere. The presence of oxygen and methane gases that shouldn't coexist unless constantly replenished would scream one thing: life. Now we're the ones playing detective, studying distant exoplanets for those same telltale signs in their atmospheres. This is the cutting edge of astrobiology, where the hunt for extraterrestrial life isn't just about finding planets in the habitable zone, it's about decoding the chemical whispers in their skies. Take Venus, our closest planetary neighbor, and a cautionary tale in atmospheric surprises. In 2020, the discovery of phosphine gas in its clouds sent shockwaves through the scientific community. On Earth, phosphine is almost exclusively produced by microbes or industrial processes, not something you'd expect floating in the sulfuric acid skies of a scorching hellscape. The implication: either there's exotic chemistry at play we don't understand, or just maybe microbial life is clinging to existence in Venus's temperate cloud layers. The debate still rages, but the lesson is clear. Atmospheric anomalies can rewrite our assumptions about where life might hide. Now zoom out to TRAPPIST-1, a dwarf star 39 light-years away with 7 Earth-sized worlds, 3 of which orbit in the Goldilocks zone where liquid water could exist. When the James Webb Space Telescope trained its mirrors on these planets, it wasn't just looking for water vapor or carbon dioxide. It was hunting for biosignatures, atmospheric fingerprints like ozone or methane that could hint at biological activity. But here's the twist: not all biosignatures are created equal. Oxygen might seem like a smoking gun, but it can also be produced by non-living processes like ultraviolet light splitting water molecules. That's why scientists look for combinations of gases, say, oxygen alongside methane or nitrous oxide, that would quickly react and disappear unless constantly replenished by something like photosynthesis or bacterial metabolism. The real challenge: distinguishing between life and false positives. A lifeless planet with volcanic activity might spew sulfur dioxide, mimicking organic byproducts. A water-rich world could have abiotic oxygen buildup from runaway photochemistry. That's where Venus's phosphine becomes so tantalizing. It's hard to explain without some form of ongoing chemistry, whether biological or geochemical. And TRAPPIST-1 planets, their compact orbits mean tidal forces could keep their interiors molten, fueling volcanoes that pump out gases capable of either supporting or obscuring life's signals. The stakes couldn't be higher. Finding even a single biosignature would revolutionize our place in the cosmos, suggesting life isn't a fluke but a cosmic inevitability. But the search is like assembling a puzzle with half the pieces missing. We're learning as we go, refining our tools and theories with each new observation. Future telescopes, like the Habitable Worlds Observatory, will analyze starlight filtered through exoplanet atmospheres with unprecedented precision, hunting for the subtle spectral lines that could reveal an alien biosphere's breath. So what if we find nothing? That's just as profound. A galaxy devoid of atmospheric biosignatures would force us to confront a chilling possibility: that life, or at least complex life, might be rarer than we ever imagined. But for now, every strange whiff of gas on a distant world keeps the hope alive that somewhere out there, another planet's air holds the answer to humanity's oldest question: are we alone? At the heart of modern physics lies a glaring paradox: two extraordinarily successful theories that refuse to speak the same language. On one hand, Einstein's general relativity paints gravity as the curvature of spacetime, a smooth cosmic stage where planets and stars perform their orbits with elegant precision. On the other, quantum mechanics reveals a subatomic carnival of particles popping in and out of existence, governed by probabilities and uncertainty. Both work flawlessly in their own domains, yet when pushed to extremes like the singularity inside a black hole or the first moments of the Big Bang, their equations explode into nonsense. This isn't just a theoretical quirk, it's a fracture in our understanding of reality itself. Unifying these frameworks into a single theory of quantum gravity isn't just academic, it's the key to unlocking the universe's deepest secrets. Enter loop quantum gravity, one of the boldest attempts to mend this divide. Picture spacetime not as a continuous fabric, but as a network of tiny, indivisible loops, a sort of cosmic chainmail woven from threads a billion times smaller than an atom. In this framework, even the vacuum of space has a granular structure, with these loops vibrating and intersecting to create the geometry we perceive as gravity. The payoff, when applied to black holes or the Big Bang, loop quantum gravity avoids the dreaded singularities, suggesting that instead of collapsing into infinite density, matter rebounds in a big bounce. It's a radical reimagining of the cosmos, where the smooth stage of relativity is replaced by a dynamic, pixelated quilt. But loop quantum gravity isn't the only player in this cosmic unification game. String theory takes an even more ambitious approach, proposing that the fundamental particles aren't points at all, but minuscule vibrating strings. Each vibration mode corresponds to a different particle: electrons, quarks, even the hypothetical graviton, the quantum carrier of gravity. Here's the catch: these strings don't dance in the familiar 3 dimensions of space and 1 of time. They require 10 or 11 dimensions, with the extra ones curled up so tightly we'll likely never detect them directly. String theory's allure lies in its elegance. It doesn't just quantize gravity, it weaves all forces and matter into a single mathematical tapestry. Yet both theories come with staggering trade-offs. Loop quantum gravity sidesteps extra dimensions but struggles to explain how the familiar, smooth spacetime of general relativity emerges from its quantum knots. String theory unifies all forces elegantly but drowns in a sea of possible solutions, perhaps 10 to the 500 variants, with no clear way to test which, if any, describes our universe. For decades, the lack of experimental evidence left both camps in a stalemate, with critics dismissing quantum gravity as untestable philosophy. That's beginning to change. Astrophysicists are scouring the cosmic microwave background for imprints of primordial gravitational waves, which could reveal quantum fluctuations from the universe's first moments. Particle colliders probe ever higher energies, hunting for signs of extra dimensions or supersymmetry, a key prediction of string theory. Meanwhile, tabletop experiments with ultra-cold atoms or finely tuned lasers might soon detect spacetime's hypothetical granularity. Even black holes, those cosmic laboratories of extreme gravity, could offer clues through their Hawking radiation or the bizarre firewall paradox at their event horizons. The quest for quantum gravity isn't just about fixing equations, it's about rewriting the origin story of everything. Did time have a beginning, or does it emerge from something deeper? Are space and time fundamental, or do they arise from quantum relationships like temperature emerging from the motion of atoms? Every unanswered question is a thread in a larger mystery, pulling us toward a theory that could reshape reality as profoundly as relativity or quantum mechanics once did. Until then, the tension between these titans of physics remains one of science's greatest dramas, a clash of paradigms where the stakes are nothing less than the universe's operating manual. Humanity's total energy consumption would barely register as a flicker on the cosmic scale, an inconsequential spark compared to the civilizations we might one day become or those that could already be out there. This is the heart of the Kardashev scale, a visionary framework dreamed up by Soviet astronomer Nikolai Kardashev in 1964 to classify intelligent species by their mastery of energy. At its core, the scale asks a deceptively simple question: how far could a civilization go if it truly harnessed the full potential of its surroundings? The answers shatter our assumptions about progress, revealing futures so advanced they border on mythology. Start with Type I, a civilization capable of utilizing all the energy falling on its home planet from its parent star, roughly 10 to the 16th watts for Earth. That means capturing every photon of sunlight, tapping geothermal vents, harnessing winds and tides, even controlling weather systems to extract maximum power. We're not there yet. By current estimates, humanity hovers around Type 0.7, still burning fossil fuels while dabbling in renewables. but the leap to Type I would be transformative, a world where energy scarcity vanishes and planetary-scale engineering becomes routine. Imagine megastructures reshaping continents or climate networks fine-tuning global temperatures. Now ascend to Type II, a society commanding the total output of its star around 10 to the 26 watts. Such a civilization wouldn't just live on planets, it might dismantle them, constructing Dyson swarms, vast arrays of orbiting solar collectors, to siphon every joule of stellar energy. Picture billions of mirrors or solar panels encircling the sun, its light systematically harvested like crops in a cosmic field. The waste heat alone would glow infrared across light years, a beacon to alien astronomers. Some researchers even propose spotting Dyson swarms by their telltale dimming in exoplanet surveys, hunting for stars that flicker unnaturally as their light is captured and repurposed. Then there's Type III, where the scale tips into the realm of gods. Here, a civilization harnesses the energy of an entire galaxy, 10 to the 36 watts or more. Whether through black hole engines, star-hopping fleets, or von Neumann probes that self-replicate across millennia, a Type III civilization would rewrite astrophysics. Their signatures might include galaxies with entire sectors gone dark, their stars dismantled for fuel, or mysterious heat signatures where waste energy bleeds into space. Some theorists suggest the absence of obvious Type III activity, known as the Fermi Paradox's Great Silence, implies such civilizations either self-destruct before reaching this stage or transcend physical forms entirely, uploading into digital realms beyond our detection. Yet the scale's most haunting implication isn't about energy, it's about time. The universe is 13.8 billion years old. That's more than enough for countless civilizations to have climbed this ladder, leaving footprints across the cosmos. So where are they? Either intelligent life is vanishingly rare, or advanced societies inevitably encounter filters cosmic roadblocks like war, ecological collapse, or technological catastrophes we can't yet imagine. There's also the unsettling possibility we're looking for the wrong signs. A Type III civilization might not bother with Dyson swarms. They could manipulate dark energy, rewrite the laws of physics, or exist as pure information in quantum substrates we're blind to. The Kardashev scale isn't just a measure of energy, it's a mirror. It forces us to confront the fragility of our own infancy while igniting dreams of what we might one day achieve, or the sobering reality that the universe's greatest civilizations may have already risen, fallen, and left ruins we've yet to recognize. Whether we're alone or simply too primitive to hear the conversation, the scale remains a challenge. If humanity survives its adolescence, will we light up the cosmos or vanish like a breath in the void? What if the universe has particles that don't just break the speed limit they were born ignoring it entirely? Meet tachyons, the hypothetical particles that exist only in the realm of what if, hurtling through space faster than light from the moment of their creation. Unlike ordinary matter, which creeps closer to light speed only by swallowing infinite energy, tachyons would have the opposite problem. Slowing down toward light speed would require infinite energy, with their natural state being a velocity we consider impossible. The implications aren't just counterintuitive, they rip apart our understanding of cause and effect, turning the cosmic rulebook into confetti. The concept emerged in the 1960s when physicists playing with Einstein's equations noticed something peculiar. If you plugged in numbers suggesting a particle had imaginary mass, yes, as in the square root of -1, the math spat out velocities exceeding light speed without breaking a sweat. These phantom particles were dubbed tachyons, from the Greek tachys, meaning swift. At first, they seemed like a mathematical curiosity, a quirk of relativity with no real-world counterpart. But then the questions started piling up. Could such particles exist? And if they did, what would that mean for reality as we know it? The answer is as unsettling as it is thrilling. Tachyons would shatter causality, the bedrock principle that causes precede effects. Imagine a tachyon signal sent from Earth to a planet 10 light-years away. From our perspective, the signal arrives before it's emitted, an effect preceding its cause. This isn't just a timekeeping glitch, it's a paradox machine, opening the door to scenarios where you could theoretically receive a reply before sending the original message. The universe, it seems, has a strict no-spoilers policy, and tachyons might be its ultimate violators. Yet for all their theoretical chaos, tachyons hold a strange appeal. Some physicists speculate they could be lurking in the quantum foam, fleeting disturbances in the vacuum of space that flicker in and out of existence too quickly to detect. Others suggest tachyons might explain dark energy, their exotic properties driving the accelerating expansion of the universe. There's even the wild possibility that tachyons aren't particles at all but disturbances in an unseen field, like ripples in a pond we can't see, carrying information faster than light without technically breaking relativity's speed limit. The hunt for evidence has been as elusive as the particles themselves. If tachyons exist, they'd likely leave trails Cherenkov-like radiation in their wake or anomalous energy signatures in particle collisions. Experiments have scoured cosmic rays and particle accelerator data for decades, but so far, no smoking gun. Some argue the absence of proof is proof enough. If tachyons existed, their causality warping effects would have destabilized the universe long ago. Others counter that we might be looking in the wrong way, like ants searching for radio waves with their antennae. Whether tachyons are a dead end or a doorway to new physics, their legacy endures. They force us to confront the limits of our models, asking whether light speed is a universal speed limit or just a speed bump for certain phenomena. And if one day we stumble upon them, it won't just rewrite textbooks, it'll rewrite history itself, in the most literal sense possible. Until then, they remain one of physics' most tantalizing ghosts, whispering from the edges of what we think we know. Galaxies are not the serene islands of stars they appear to be. They're cosmic predators, locked in a slow-motion battle for survival where the strong consume the weak. This violent dance, known as galactic cannibalism, unfolds over billions of years, shaping the universe as we know it. Picture a vast cosmic web where galaxies, pulled by gravity's inexorable tug, spiral toward one another until the larger engulfs the smaller, tearing it apart in a spectacle of stellar destruction and rebirth. Andromeda and the Milky Way, our own galactic home, are destined for this very fate, a collision course set in motion the moment both galaxies formed. The process begins with tidal forces, the gravitational equivalent of a cosmic tug-of-war. As a smaller galaxy drifts too close to a larger one, the difference in gravitational pull stretches and distorts it like taffy caught between two hands. Stars and gas are ripped from their orbits, forming long, shimmering streamers called tidal tails, celestial breadcrumbs marking the victim's demise. The Milky Way itself is no stranger to this violence. Look no further than the Sagittarius dwarf spheroidal galaxy, a tiny neighbor currently being torn apart by our galaxy's gravity. Its stars are already scattered across our skies, absorbed into the Milky Way's halo like a ghostly fingerprint of past feasts. But the impending collision with Andromeda is on another scale entirely. Located roughly 2.5 million light-years away, Andromeda is hurtling toward us at 250,000 miles per hour, drawn in by the mutual pull of dark matter and gravity. When they meet, in about 4 to 5 billion years, the two spirals will first pass through each other, their stars so far apart that direct collisions are unlikely. Instead, gravity will twist their shapes into chaos, flinging stars into new orbits and igniting bursts of star formation as gas clouds compress. For eons, the galaxies will loop around each other in a cosmic ballet, their structures unraveling until they merge into a single, colossal elliptical galaxy. Astronomers have already nicknamed this future hybrid Milkdromeda. What's fascinating isn't just the destruction, but the creation that follows. galactic mergers are stellar nurseries on a grand scale, where the chaos of colliding gas clouds births millions of new stars. The Triangulum galaxy, caught in Andromeda's gravitational wake, may join the fray, turning the event into a three-way showdown. Yet amid the chaos, individual stars will likely survive unscathed. The distances between them are so vast that even in merger, solar systems remain untouched. Earth's night sky, however, will transform into something unrecognizable, with Andromeda's stars painting streaks of light across a darkened heavens. This process isn't unique to us. Across the universe, galaxy clusters are built on the remains of countless mergers. The giant elliptical galaxies at their cores, like Messier 87 with its infamous black hole, are the products of billions of years of galactic cannibalism. Each merger leaves clues, distorted shapes, rogue star clusters, and even shell structures, concentric ripples of stars left behind like echoes of a devoured galaxy. The universe, it seems, thrives on this cycle of destruction and renewal, where galaxies grow not just by forming stars, but by consuming their neighbors. So while the Milky Way's fate seems violent, it's also inevitable, a reminder that even the cosmos operates on the principle of survival of the fittest. And when the dust settles, what emerges from the wreckage may be even more magnificent than what came before. The cosmic microwave background is supposed to be the universe's most democratic feature, a near-perfect snapshot of the infant cosmos, its faint glow radiating equally from all directions. But when scientists mapped it in detail, they stumbled upon something that shouldn't be there, a bizarre alignment of hot and cold spots that seemed to point toward a specific region of space. This peculiar pattern, nicknamed the axis of evil, isn't just a statistical fluke. It hints that the universe might have a preferred direction, a cosmic north that defies everything we thought we knew about the fundamental symmetry of space. This anomaly first came to light with NAS, a Wilkinson microwave anisotropy probe, which revealed that certain fluctuations in the CMB weren't randomly scattered but oddly aligned along a particular axis. Later, the Planck satellite confirmed the finding with even sharper precision. It's as if the universe rolled a loaded dice, with the temperature variations lining up in a way that suggests structure where there should be none. According to the standard cosmological model, the Big Bang's afterglow should be isotropic, uniform in all directions, with no special orientation. The axis of evil shatters that assumption, whispering that the cosmos might be oddly lopsided on the grandest scales. Theories attempting to explain this alignment range from the provocative to the downright revolutionary. Some suggest it's an artifact of our local environment. Perhaps the gravitational pull of a nearby supercluster is subtly distorting our view, like a fingerprint smudged on a telescope lens. Others propose more exotic explanations, like the imprint of a universe that existed before the Big Bang, its ghostly structures tugging at the fabric of our own. Then there's the radical idea that the axis of evil could be evidence of a multiverse, with neighboring universes brushing against ours and leaving gravitational scars in the CMB. But the most unsettling possibility is that we're seeing the limits of our own understanding. The cosmological principle, the bedrock idea that the universe is homogeneous and isotropic on large scales, might not hold as universally as we assumed. If the axis of evil is real and not just a measurement error, it could mean that the universe has a fundamental asymmetry, a hidden grain like wood that breaks differently depending on how you cut it. This would force us to rewrite textbooks, rethinking everything from the distribution of galaxies to the very nature of cosmic inflation. For now, the axis of evil remains one of cosmology's greatest unresolved puzzles. Is it a statistical mirage, a cosmic illusion soon to be dispelled by better data? Or is it the first crack in a foundational theory, a sign that the universe is far stranger than our models can accommodate? Whatever the answer, this anomaly reminds us that even our most cherished assumptions about the cosmos are provisional, and that the deepest mysteries often lurk in the details we least expect. From the ghostly grip of dark matter to the universe-shattering potential of vacuum decay, these 30 theories aren't just wild guesses, they're the bleeding edge of human curiosity, each one a testament to how much we don't yet understand. Think about it, black holes might be gateways, consciousness could shape reality, and the cosmos itself might be a holographic projection. Even the empty space around us isn't truly empty, but a seething quantum foam where particles flicker in and out of existence. And that's just the tip of the cosmic iceberg. What makes these ideas so thrilling isn't just their strangeness, it's the way they force us to confront the limits of our knowledge. Every unexplained phenomenon, every paradox is a crack in the facade of what we think we know, and behind those cracks lies a universe far weirder, more intricate, and more mysterious than we ever imagined. The great attractor tugs at galaxies we can't see, zombie stars defy death, and alien civilizations might be hiding in plain sight, their signals lost in the noise of the cosmos. Even time itself might not be what it seems, with crystals that pulse in rhythmic loops and particles that dance to quantum beats we're only beginning to decode. This isn't just science fiction. These theories are grounded in math, in observation, in the relentless human drive to ask why, and then chase the answer, no matter how bizarre the path becomes. Some will be proven right, others will collapse under the weight of new evidence, but every single one pushes us forward, reminding us that the universe isn't just a puzzle to be solved, it's a story we're still writing, one discovery at a time. So stay curious, the next cosmic revelation could be hiding in the next anomaly, the next burst of radio static, the next flicker of starlight, and who knows? Maybe you'll be the one to spot the clue that unravels it all. If you're as hooked on these mysteries as we are, hit subscribe, because the universe isn't done surprising us, and neither are we. The journey's just getting started.